Okay, so welcome to the final Chandrasekhar lecture by Rob Myers. Before I get all emotional at the end of the talk, I think we should begin by thanking Rob for what will evidently be 3 beautiful lectures. So he's going to tell us about entanglement and C-theorems.
You should save that for the end. Sure. So as the title indicates, I'm jumping a little bit, but this is an idea that I talked about towards the end of the first lecture in the colloquium. So entanglement and C-theorems. Here's an outline, some introductory remarks. Then I'm going to talk about holographic C-theorems, entanglement entropy, and new C-theorems. Progress beyond holography, and then going beyond entanglement entropy. And as is traditional, I've got one slide of conclusions, and in this case, questions. So let's get started. All of this has to do with renormalization group flows. And so in my colloquium, I drew pictures like this. I stole that from the colloquium slides, and I had a definition here. The renormalization group is a mathematical apparatus that allows the systematic investigation of changes of a physical system as viewed at different energy or distance and energy scales. So since that's the bedrock of what we're talking about, I just wanted to make sure that I give you a flavor for what it is that picture actually represents, just to make sure that again, I'm not exactly sure what the background of everyone is, but I wanted to make sure that we can, you can follow along at least part of the talk. So renormalization, or the renormalization group, actually has a long history. It goes back to the 19th century, although they didn't call it that at the time. At that time, they were thinking about turbulence and making effective theories to describe the hydrodynamics of fluids. But it came to the fore in the 60s, I guess, in the study of phase transitions and also particle physics. But the classic example I'm going to use here is just some system of spins. So I have a lattice, and there's a spin at each site, and we can imagine that the lattice extends forever. Except I don't have enough room to draw a forever lattice. And on that lattice, I'll put some Hamiltonian that talks about the interactions of nearest neighbor spins. So this indicates that I'm only got interactions between spins on neighboring sites, as indicated by the red arrows there. Now, in the renormalization group, what I'm going to do is I'm going to block the spins. I'm going to take blocks of the spins in my lattice, and I'm going to replace each one of those blocks by an effective spin. So I get this lattice. So this picture becomes this picture down here, where each one of the big X's is now an effective spin. And in doing that, I have to come up with a new Hamiltonian to describe the same physics here, but using this set of variables. And in general, I'll get something that looks like this. So I've got the interaction here between nearest neighbors in the new lattice, but the coupling constant is going to have changed in principle, so that K0 became a K0 prime. But in general, there's no reason to believe that the Hamiltonian is going to take the same form that it did up here. And so there might be new kinds of interactions. So this is a next to nearest neighbor interaction between sites along the diagonals of our square. Or there might be interactions involving plaquettes, as here. So this interaction or contribution to the Hamiltonian involves all 4 around a square like that. And I've written a ... because you can be creative and write down lots of other interactions. And so the idea is that this Hamiltonian is going to capture or give us the same physics as this, but with a new set of variables described on this lattice. In general, what this shows me is that when I'm thinking about the Hamiltonian, the original Hamiltonian that I wrote down was very special with only the nearest neighbor interactions. But in general, I have a whole collection of all sorts of couplings that could appear describing interactions of spins. And under this blocking of spins and decimating the lattice or going to a coarser lattice, What I explain, or what I hand-wavy explained, is that the couplings change. So in general, I'm going to have some set of couplings. I'm going to implement one set of blocking of the spins, and I'm going to go from that set mu to some new set mu prime. And can I just finish my paragraph? So doing that in a systematic way is basically what the renormalization group is all about. And we get these pictures. This is supposed to be the space of couplings. And as I do my decimations, I'm moving around in that coupling space. But Barry had a question.
Yeah, when you, so if you have spin-half systems, and then you create cats, do you have to deal with a higher spin?
In principle, it depends on how you want to approach the procedure. But let's say for now that I'm not going to do that. And I'm going to try and capture the physics just with having more complicated interactions. But in principle, you're saying, you know, there are 4 spins here, and that block could have had anywhere from spin, I guess, 2 down. So right, yeah. But, well, I'm not, generally, I think we don't do it that carefully. We're not going to do it that carefully. But, yeah, okay, I'll just leave it at that. So this was just to give you a flavor for what I'm talking about when I draw pictures like this, or I say the words RG flow. What the word in the title was the idea of a C-theorem, and this goes back again to 1986 and Mr. Zamlogikov. Okay.
Did people in the 19th century actually define some sort of RG flow without under another name?
To tell you the truth, my history is not adequate to answer that question. That just comes from the introduction to some book I was reading. Hopefully. No, but the idea of coming up with replacing or coming up with a coarse-grained, or the idea a coarser effective theory is an older idea, and that. Well, I was claiming that it goes back to ideas in studying turbulence already in the 19th century, that people played or did that kind of thing. They didn't go by this name, but that it's something that physicists have done for a long time.
Just another question, which is that in your, I mean, to do this RG thing, you need to also assume that the system is extensive at some level, that if you had long-range interactions, can you do the same kind of thing?
I'm sure there are all sorts of details that I glossed over, and again, I'm not.
You're saying that the whole procedure is irrespective of couplings and.
Is irrespective of coupling.
Meaning long-range interactions and so on. So when you have,
in principle, you know, I mean, in principle, there could be very long-range interactions. The hope is that, you know, I wrote a list with a ... but the hope is that most of those interactions are irrelevant, and that I'm going to be able to describe the physics with just a few parameters. I mean, that's the idea. Well, that's why this works. If it was really an infinite dimensional coupling space, which I can certainly write down, if all of those terms were important, we're not making much progress. But the idea is that most of those interactions are irrelevant, and that when I flow down, say to, where is it? To one of these critical points, that it's only, you know, 1 or 2 or you know, a small number of the parameters that are really controlling the physics. What Zamlogikov was talking about was 2-dimensional quantum field theories, and he was looking at renormalization group flows there. There are lots of equations and lots of structure here, but again, the basic idea, or the essential thing that he discovered, is that there's an elegant function, which I'm calling the C function here, that lives on the space of couplings. And that C function satisfies a number of properties here. Again, I'm not going to go into the details, but the idea that I conveyed in my colloquium is that this picture of the RG flows becomes a landscape, that the C function provides us with a number that we can associate to all of these points, and also that as I follow the RG flows, that I'm always flowing downhill in this landscape, or that my C function is decreasing. So a simple consequence of that is that if I evaluate the C function at two fixed points that are joined by an RG flow, that, well, a comment is that the C function here plays a special role at the critical point in the conformal field theory here. It's known as the central charge, of course, but the central charge at the high energy or the UV end of the flow is bigger than the central charge at the low energy or infrared end of the flow. So that's just one consequence of all of that structure that we had on the previous transparency, but that's really what I'm going to focus the discussion on today in other contexts. So what does this idea have to do with entanglement? Well, as it was originally presented, entanglement was nowhere in the story. However, as I mentioned in the colloquium, Cassini and Huerta, 8 years later, reformulated the proof of the C-theorem in terms of entanglement entropy. And so they used the basic ingredients of unitarity and Lorentz invariance, but then they also use this idea of strong subadditivity, which is some inequality of satisfied by entanglement entropies. So given that I have lots of time today, I wanted to talk about that in a little more detail. And so how does this discussion go? Well, first of all, we know that in a two-dimensional CFT, if I calculate the entanglement entropy for a single strip, I get an answer that looks like this. And I guess we've seen that in various lectures. But there's a logarithm here with the size of my strip and a cutoff. And the coefficient here is precisely the central charge divided by 3. There may be some non-universal stuff depending on how I did the calculation, but this is independent of the geometry. Now, if I look at that formula, I can easily see that there's a way to extract the central charge by taking a derivative of the entanglement entropy. Then that gives me a 1 over L, and then I multiply by L to get rid of that, and I stick in a factor of 3, and the answer is precisely the central charge C. And so what they did is they said, well, for a general field theory in a general context, I'm going to define this as a C function. I'm going to calculate this quantity for arbitrary values of L, and I know that when I'm sitting at a critical point, or when I'm sitting at CFT, that C function is going to give me the central charge. One thing to note here is well, I guess I didn't go through any of the details, but the standard discussion of renormalization group in particle physics or on HEP-TH is one where you refer to energy scales. And here I'm using the length of the interval as a proxy for energy scales. So certainly the entanglement entropy is probing different scales as I vary or different sets of degrees of freedom as I vary the size of the interval. And that's, of course, intuitive. There's the usual idea that length is roughly 1 over energy. Oh, question.
Central charge is uniquely defined only at the fixed point where there is a conformal region. In the intermediate region, the theory is not conformal. So how will you define a central charge? Or
No, I'm not doing that. I'm defining a flow function or something that's going to vary along the RG flow. That's this. And that quantity, when I hit a fixed point, either for very small intervals, say when I'm at near the UV, or for a very large interval when I'm in the IR, that flow function or that C function becomes the central charge of the associated fixed point.
That is okay, you can take this particular definition, but is it a unique way of defining it? That's what I mean.
No, if I give you a flow function, I can square it, and I have something that flows as well. I mean, this isn't a unique definition, and so, well, there's a bit of sociology is that originally they thought they had invented a new C-theorem, but it's really the same C-theorem that they're proving. Not yet. No.
So you're going to use that, right?
Yes.
Okay.
I told you I'm going through it in more detail. Have we gotten to it yet? No. Okay. So settle down. So we've defined a flow function or a C function. Okay. What's the other question? You know, I really want to get to the end today, though. So anyway, what's your question, Raphael?
So
Oh, Barry. Okay.
me,
go.
yeah. So I'm feeling intimidated, but I'll ask anyway. It's just a stupid question. I'm trying to grasp it, but I understand the SCFT you've got there. Down below, you define the charge. So I can see that when you do the derivative with respect to L, C is going to be a constant. But if S is not logarithmic, then
Yep.
does C become L dependent?
Yes. That's why there's a little L.
Oh,
there.
little c, I mean, little c.
The little c.
Yeah, you've defined a charge that to me seems quite sensible if entropy is logarithmic.
Right.
That's always the case?
Sorry, we'll try again. So the idea is that if I'm studying a conformal field theory, this is the answer. And then I get that. And so the observation is just that if I define this in general, when I get to a CFT, I'll get the answer that I wanted. I'll get the charge that I wanted. In general, I'll get other stuff here, and this varies as L changes, and so I get other numbers. But that's okay. Raphael?
No, I didn't have a question. I was
Oh.
finding out the very
Oh, okay. Sorry.
You got scared.
So that was the first observation. So now I'll make another a set of observations. First of all, okay, so I want to do this in a Lorentz invariant context, and so I've got some intervals. Well, I'm going to be thinking about lots of different frames or time slices. And so the observation is that if I think of an interval defined by two endpoints, it doesn't really matter what the time slice is or what the Cauchy surface is on which, say, I'm evaluating rho of A. That rho of A is going to tell me about all of the physics in here. And the details of the entanglement entropy that I calculate are going to be, no, I said that wrong. The entanglement entropy that I evaluate here, say for the blue curve or the red curve, is going to be identical. It's not going to depend on the Cauchy surface because I'm just going to use unitary evolution to carry my density matrix from one to the other. Further, if I have translation invariance, then I can argue that this entanglement entropy should just depend on the proper distance between these 2 points. And so it should be a function just of, well, some expression like this. So taking those ideas, now I'm going to apply strong subadditivity, but I'm going to apply it to this particular picture here. And so I don't know, can I explain the picture, or do you want to ask the question first?
It's not related to this picture.
Okay.
The question is related to the strong subadditivity proofs that I've seen are in quantum mechanics with the finite dimensional Hilbert space. But is it straightforward to extend it to quantum field theories?
Is it straightforward?
So there must be some caveats there that we don't explain.
That, the answer is yes. Okay. So,
Are you going to truncate the Hilbert spaces at very high energy? That is theory in truncate. In that case, it's just kind of
yeah, okay. Okay, I don't want to get in an argument about this because I admit, I'm lying. Look, there's a cutoff in the answer, right? And there's actually an issue there. And if we get to slide 54, I will talk about that. But for now, you know, there are caveats, but in principle, what I'm doing is I've cut things off, and so it is finite. But that's a subtlety, but I'm just going to gloss over it. Right now, I'm going to look at this picture. So what do I have here? I have an original interval y that has some length L. Then I have a light cone here that's tangent to the two endpoints. And so I go up to a second interval from my time slice t equals 0 to the time slice t equals epsilon. Now I've got an interval here that's length L plus 2 epsilon. And in defining my regions that I'm going to plug in to the strong subadditivity, I'm going to take my original interval y, and then these two intervals y and z are extending along this portion of the light cone here and here. Well, let's evaluate the various terms that appear in my inequality. Here I'm going to get an S of L. Here I'm going to get an S of L plus 2 epsilon. For y union z, that's this slice, I said that the entropy doesn't depend on the particular choice of my Cauchy surface, and I can just, or alternatively, it just depends on the proper distance between those 2 points. And so you can just calculate, and what you find is that I can write the proper distance or the proper separation between those 2 points as L times L plus 2 epsilon. I mean, it's basically, it was L plus epsilon squared minus epsilon squared, and so you got an S, well, square rooted, and so you got that answer. And so strong subadditivity, if I just plug in there, says that these two, the sum of those two entropies is minus this particular entropy, gives me a result that's less than or equal to 0. Or there was, well, 2 there because both that one and that one are the same by the symmetry. So now what I do, or what they did, is they said, let's consider the limit where epsilon is going to 0. Then the 0th order term cancels because this becomes S of L, and then these are both S of L, so I'm subtracting that. That gives me a 0. If I expand the first order in epsilon, it turns out that the contribution here and the contribution here also cancel. But there's a non-vanishing, or the first non-vanishing contribution is that order epsilon squared, and it looks something like this. There's an S double prime. Well, there was a bit over here as well. And then there's an S prime over L, which comes because I had to expand the square root as well as expanding the S. But if I massage that a little bit, I can see that that's just the derivative of L times the derivative of S. And that was precisely what we defined as our C function. And so what this inequality says is that the derivative of the C function is less than or equal to 0. That is, if I take my interval and I start increasing it, the C function gets smaller and smaller and smaller. And so if at short scales I have the UV fixed point, and what it gives me is the central charge of the UV conformal field theory. At very large scales, I get the IR central charge, and they're going to satisfy an inequality that says the UV central charge is bigger than the IR central charge, and I guess that's what's written here. So I'll pause there. Are there any questions about that? I just wanted to show a little bit of detail because there are 2 stages where there's a much more complicated proof, and I'm not going to tell you any of the details. I'm just going to draw pretty pictures and say it all works out. But this one is simple enough that you can follow through. And so it's an interesting paper because this is a profound result about renormalization group flows and quantum field theory, but the discussion all involves just geometry, Lorentz transformations, and this inequality. Raphael.
Is there any connection between the value of their C function and Cosmological C function in between the fixed points?
There's not a simple mapping from one to the other, no. No. And that may become obvious on the last transparency if we get there.
What about theories which don't have Lorentz inversions?
This doesn't apply. That was an easy one. Other questions? No, that's what I referred to as just on the last transparency. So let's not worry about that now. For the people who are specialists, and since we might not get there, what he's referring to is that one of the criteria, or one of the nice features of Cosmological C function is there are three properties here. One is the monotonic flow, but there's also this stationarity. And then there's the fact that it matches the central charge. So what I showed you was something about monotonic flow and matching the central charge, but it turns out that this is not always satisfied, that when I sit at the fixed point, it's not always stationary. But let's not worry about, well, okay, for the people, if that's not something you appreciate right away, let's not worry about it. We've still established this corollary just using the entanglement entropy. That was the idea. Oop.
Sorry, I have a question.
Okay.
You're using strong subadditivity to derive this result. So this S function, S is an entanglement entropy or not?
As
Generally.
I presented it, it's just the entanglement entropy of various interval, of a single interval, yeah.
Okay, so you are now focusing only on the entanglement entropy S, right?
Yeah.
Okay. And I have another question. So you derive a general result delivered to C with respect to L is negative. So this L is automatically correspond to our renormalization scale.
Well, that's what I said. In this discussion, I'm using L as a proxy for energy scale. And intuitively, that makes sense. I mean, we're used to the idea that large distance scales correspond to low energy, short distance scales, high energy. And so it's in that sense that I'm making, just because of the geometric construction, it's natural to discuss it in terms of the size of the system or the size of the interval.
Okay.
Okay, let's see. So, as I also said, this went largely unnoticed at the time. What people, though, were thinking about were, are there C-theorems in higher dimensions? And so there, to make progress, one has to think about what is the role of the central charge in a two-dimensional quantum field or conformal field theory. And in fact, it has many different roles. But one that seems relevant here is that it appears in the trace anomaly. So in any conformal field theory, if I ask what's the expectation value of the trace of the stress tensor, the answer is 0 because this is roughly an energy density. So an energy per, well, here it would be an energy per length. But the thing is, I said that I had a theory with no scales in it, and so there should be no answer that I can put on the other side. And so in flat space, that's correct. This quantity vanishes. But if I take the theory and put it on a curved manifold, then it's not quite 0. Rather, I get this rather elegant thing, where this is some geometry, that's the Ricci scalar, and then there's a factor here, which involves precisely the central charge. And so I can think of that as a way to identify the central charge through what's called the trace anomaly. I can then, the goal is here to think about higher dimensions, and so this idea extends to higher dimensions. In fact, it extends to any number of even dimensions. And so in 4 dimensions, I get an expression like this. I have more geometry. There are more complicated expressions that I can write down here. And in fact, I get 3 quantities that I can think of as central charges in a four-dimensional conformal field theory. And so the question is, do any of these three quantities satisfy a nice monotonicity or satisfy something like Cosmological C-theorem, i.e. that it would always be bigger at the UV end of an RG flow than at the IR end. With counterexample, or just demonstrating an RG flow where this inequality is not satisfied for the central charge C, that one can be ruled out. There also, there's a more subtle discussion about this particular quantity. This isn't really a universal coefficient here. I can change it depending on my regularization scheme. And so this is not really defined over the whole space of, well, over the RG flows. And so this isn't seen as an appropriate quantity either. And so that leaves us with one central charge A in 4 dimensions. And it was actually Carty who got in first and suggested that that should be the central charge that satisfies, well, an A theorem. And so over the years, there were lots of non-trivial examples where one saw that A was always larger in the UV than at the IR. There was even some work in holography, or using the ADS CFT, showing that that property held. And I'll come back to that in a moment. But then, you know, progress kind of petered out. But the idea is, the reason I'm giving this lecture is that there's been a lot of advances in recent years, both from holography and outside of holography, and thinking about not just 4, but other numbers of dimensions, in particular 3 dimensions. And so I think that's the end of my introductory remarks. So,
terms which are over there, are they separated by some invariance properties?
Well, they're each associated with a different kind of geometric factor. So if I think about not a single geometry, but if I vary the geometry, I'll get different numbers here, and I can identify, you know, which coefficient is associated with which
so there are
expression.
different invariants based on some geometric properties.
Yeah, yeah.
Question.
Sure.
The previous talks, you restricted to flat space-time theory?
This discussion was all in flat space, yeah.
So all this was, but then you're transiting now to curved
Yeah,
space.
when I prove the C-theorems or talk about the RG flows, I'm always going to be in flat space. This was just a way of saying, well, where do I find interesting quantities in the theory that might satisfy an RG flow? And so this was a place where I see C appears in 2 dimensions, and these are the sort of the counterparts for a 4-dimensional. And that involved some geometry. Other questions? Wow, okay. Holographic C-theorem. So I just want to review, well, some early work that goes back to, say, around 2000, and then the more recent work that I did with Aninda. Here again, the playground is the ADS CFT correspondence. I've got a boundary conformal field theory and some kind of gravity theory in the bulk, and those are 2 different descriptions of the same physical phenomena. Again, I'll remind you, here what I'm describing with a cosmological constant is one particular conformal field theory. When I have RG flows, I want to have something with lots of, or the potential to have lots of different conformal field theories connected by RG flows, or lots of different critical points. A simple way to do it, or a cartoon here, is that rather than having a cosmological constant, or a constant negative energy density here, I'm going to couple the geometry, or Einstein gravity, which is represented by that, to a scalar field, and I'm going to give the scalar field some interesting potential. And that potential has stationary points, and by construction, they're all negative. And so if I sit at one of the stationary points, I've got a negative energy density, or a negative cosmological constant, and the solution for the gravitational equations is, again, going to be ADS space, although the curvature scale is going to differ between these 3 points. And that's partially indicating that at those 3 points I'm describing different CFTs. So this is a cartoon. In the original papers, people looked at sort of more top-down constructions where this kind of emerges from string theory or from supergravity. And it's not just generally it's not just a single scalar field or a simple potential like that, but it can be something more complicated with lots of scalar fields. The holographic RG flows then are solutions that interpolate between two of these stationary points on the potential. And so the idea is at large radius, or in the UV of the boundary theory, I'm close to, well, one particular stationary point, but then the scalar, as I move in radius, rolls down, and I end up at some other stationary point at small r, or in the infrared of the corresponding boundary theory. And so a lot of what they did in these papers, these original papers, was establish the fact that flows like that, or gravitational solutions like that, actually existed. Looking at it in a little more detail, here's the metric that one considers. So I put here, I just have a flat space metric for my boundary theory, and I put all the interesting geometry into one factor that sits out here. If I'm in an ADS vacuum, it turns out that that function is just linear, r over the curvature scale of whatever the ADS space is. And so I'm going to, in a moment, just do something that involves building something out of that conformal factor, or that A. So as I said, a lot of what they did is spent their time showing that solutions like that actually existed, but a corollary or an outgrowth that they mentioned in the papers was the following. So this is that conformal factor that appeared in the metric. If I take the derivative with respect to r and then plug it into this construction with some prefactor, and there's a certain power, that defines some function that varies as I move through the radius in these solutions. And if I consider the derivative of that with r, I get an expression like this. But then I look at the gravitational equations of motion, and I find that this expression is connected to this expression, where this is now the stress energy tensor of the matter fields in my gravitational background. It turns out that these components, this is something that gravitational people have studied. If I have an expression like that, it turns out that should always be negative. That's something known as the Null energy condition, which says that if I take the stress tensor of a reasonable field theory, or a reasonable matter theory, and I couple it with any two null vectors, I should get a number that's greater than or equal to 0. Or that's actually backward. No, that's right. But up here, it means that this quantity is negative, but that combines with that minus sign there, so that this is positive. And so what I've shown is that this flow function, or this thing that's varying with r, its derivative is always greater than 0. So if I start at small r and I work my way up through the solution, it's going to start with some number at small r, and it's going to be bigger when I get to large r. So that has very much the sound of a C-theorem, in that I know that moving through r I associate with moving through energy scales in the boundary theory. If I think, well, okay, this is just saying if I evaluate this at the stationary points, I get something like this. So remember, this was just linear for an ADS space, and so taking that derivative gives me this curvature scale. But what I just said is this is always going to be bigger at the large r, or at the UV end of my solution, than it is at the small r, or the infrared end. I can also look at my ADS CFT dictionary, and I realize that this particular combination of things is actually the central charge A in my boundary theory. And so this really is matching up to Carty's conjectured A theorem. It says that for all of these holographic theories, A is bigger at the UV end than at the IR end of these holographic RG flows. A comment is, though, that in Einstein gravity, it turns out that A and C are both equal. And so this is also saying for this particular class of theories, it's also going to be true that C is bigger at the UV end of the flow than the IR end of the flow. Well, I'll pause. Are there questions? Yes? Yeah, this is only, I mean, this is described, well, by definition, I'm looking at this holographic theory that I wrote down on the previous transparency. And so we're only talking about these, you know, some class of strongly coupled quantum field theories that have a holographic dual. So it's a very special kind of field theory.
Within that strongly coupled restricted regime of the parameter space of couplings, you're able to see these flows. I mean, that's...
Yeah.
You're talking about 1 over n corrections.
1 over n corrections. Maybe, so this is large lambda in the field theory. So I'm saying if it was some intermediate lambda, because like if it flows, you don't know to which lambda to it flows to. It might be flow to a smaller value of the coupling. Like, whereas
yeah,
like
no,
if there is a holographic description.
Yeah, again, I'm looking at holographic theories. So by definition, I'm talking about one of these, I mean, I'm talking about a theory that has a representation in the gravity side. You know, this is representing the physics of that boundary theory. I use this as my tool. So it's a special class of theories. You know, one property that makes them special is, well, something that is special is those two central charges are always equal. But then part of the, well, again, I said this before, I'm a string theorist. Oh, I should have, were there other questions?
Sure, all those coefficients you call central charges, that are A, C,
Yes.
and possibly A prime.
Yeah. That's the nomenclature, and I'm going to call other things central charges, but it's for me, that's just something that's giving me a count or some reference to how many degrees of freedom. In particular, when I get to odd dimensions, I can't say that it's really the central extension of some algebra. Okay, I'm a string theorist. I'm happy to think about theories in any number of dimensions, and so it just becomes a dial in the construction. I think about a d-dimensional boundary theory. That means I have a d plus 1 dimensional bulk. So there's a d that appears here, but roughly the story goes through unchanged. I write down the same kind of metrics with this conformal factor A appearing there. I can define some quantity like this, which is the flow function, and I can use the gravitational equations and the null energy condition to say that that flow function is always increasing as I go up through my bulk space-time. And so at the state, if I think about evaluating this at the UV end and at the IR end, I always get a bigger number at the UV end than I get at the IR end, i.e., or it's bigger at large radius than it was at small radius. I can also use this technology to relate this quantity to various central charges that appear in the trace anomaly. Or at least I can do that for even dimension or even Ds when the boundary theory is even dimensional. But there's nothing in this construction that said D had to be even. In fact, I could think about this construction for D odd and for, well, people may have asked the question, but they never answered the question, what would that correspond to if I had an odd dimensional boundary theory? It seems that we have something that looks like a C-theorem, but it was something for some reason that people didn't talk much about. One of the, here I just said, is very, or looks like a central charge in the trace anomaly. again, I'm studying Einstein gravity, or a particular gravity theory. It turns out that, again, all of those central charges are the same. And so the central charges are flowing, but I can't really say that I'm favoring one kind of C-theorem over another, or that definitively it's a particular central charge that has the monotonicity. So Ananda and I were impatient, and we wanted to think about theories where we could actually distinguish the different kinds of central charges. And it's something that had long been known, or when we got there, it would have been long already. People had discovered that if I want to think about a boundary theory where, for example, A is not equal to C, then in the bulk, I would have to add or think about a gravity theory with higher curvature interactions, say a curvature squared interaction. So I'd have to go beyond just Einstein gravity. And so what I'm going to think about next is constructing some toy models of such higher gravity theories, but I'm going to pick ones where the calculations remain under control. And I'll be clear about what I mean by that and what particular models I'm going to use in a moment. The string theorist should be worried. I'm inventing some theory. How do I know that it's realistic in any way? Well, one thing you can do is you can try and constrain the couplings in your theory so that the physics of the boundary theory is reasonable. And there are various things that we thought about, various tests or constraints, but ultimately there's this very dangerous use your best judgment. And then I have to, in order that I don't get kicked out of the club, I have to say that ultimately one needs to develop a full string theory in such interesting holographic backgrounds where I'm describing boundary theories where this is, those central charges are not equal. But we also, well, a slogan you might put forward is that if there are certain characteristics that are going to be true of all CFTs, then these holographic toy models should also exhibit the same features. So here's our favorite, or a model that we looked at. Essentially what I have here is my negative cosmological constant. This says that here's a geometric term. That says I've got an Einstein-like term. Here I've got some expression that involves curvature squared. For the specialists, that's the Gauss-Bonnet term. Here I've got an expression that's got curvature cubed. That, for the specialists, again, that's not the Lovelock term. And so ultimately I've got I've embellished my gravity theory. I now have three couplings. I've got the ratio of the curvature scale to the Planck scale. That appears, for example, in central charges. I've got this coupling lambda, and I've got the coupling mu for the curvature cubed. What did I mean when I say calculations are under control? Well, this is a nice theory in many respects. The reason I originally constructed this with Brandon was that, in fact, you can find all of the black hole, the ADS black hole solutions in this particular theory, and that was important for something else that we were doing. I was actually perplexed why we could find all of the solutions, but it turns out that the equations are actually much simpler than you might originally think. And if I think about the linearized gravitational equations of motion, in fact, even though I have this complicated, curvature cubed, curvature squared, the equations of motion are second order. And in fact, they correspond up to some overall coefficient to just being the Einstein equations. Again, that's the linearized equations. But that makes life easy. It means a lot of the calculations that one does with Einstein gravity just get, you get to do them over again, basically for free, just keeping track of some extra constants. Another comment is I wrote this down for D equals 5, a 5-dimensional bulk, 4-dimensional boundary, but you can extend this to higher dimensions as well. And you can also think about these constraints for these couplings that I talked about. And so here's a picture of some constraints. I won't explain where it comes from, but you have to live inside this red triangle, and you can see that the lambda coupling and the mu coupling can't get too large. So that's some 4 years ago. People have thought about this more recently again. Well, not our particular theory, but thought about these kinds of toy models more recently. And something that was suggested was perhaps we can get tighter constraints as follows. Implicitly in all of my discussion, I'm going to focus on a set of solutions which reduce down to Einstein gravity if I take the limit lambda and mu going to 0. Typically, there are other branches of solutions which wander off to infinity in this limit. But the problem is that most of those solutions, or many of those solutions, are pathological. By which I mean, well, for example, the gravitons, rather than having positive norm, they're actually ghosts. So this was something that was noted long, long ago. And that's why we focused our attention on this particular branch of solutions. However, these folks suggested, well, if I really want to take this seriously as a quantum theory, I'm going to get tunneling between these various branches. And so what they did to invent tighter constraints is they demanded that there not be any tunneling from the nice vacuum, from this branch, to one of these pathological branches. And so they looked at various examples and showed that the constraints were actually tighter than on this transparency. Well, in particular, they were looking at this axis, and so they ended up with a tighter set of constraints along that axis for the lambda parameter.
When you say that there's no tunneling, does it mean non-constructive? What does that specifically mean? There's no tunneling?
We'd have to go look at the paper. I can't describe in detail this morning what I mean, it has to do with that. I mean, they looked, I forget what went into the wall. There's some distributional, I mean, but yeah, what they did is they looked at constructions of instantons, of bubbles coming out of the vacuum, and then they showed in certain regimes they would just collapse again rather than expanding, something like that. So.
When you said that you constructed all Lagos, do you mean that somebody has demonstrated the Birkhoff theorem in these theories?
I guess we did, yes. Yeah, no, I guess so. Yeah. Yes. Something that's irrelevant to my talk, which will never end. Ask me afterwards. Even more recently, this summer, there was another paper that considered these causality, they thought about causality violations. I mean, there's another way, or their discussion involved, again, looking at, if you like, the linearized or perturbative theory around your ADS space. And what they noted is that sticking in these higher curvature interactions modified the three-point vertex for the graviton. Even though the kinetic term was the same, when you look at the three-point term, you can see that this is a different theory, and that makes sense. But they argued that if the three-point vertex was modified from what you see in Einstein gravity, that actually will lead to causality violations in your bulk theory. But they went on to say that perhaps that can be resolved by introducing, in fact, an infinite tower of higher spin fields. But the masses of these fields would be of the order of the curvature scale in your theory. And so that's saying that, well, I can play with this model, but I have to accept that it's an incomplete model and that there must be other degrees of freedom to make it into a real theory of gravity or quantum gravity. Yeah.
This tunneling question, see, but if you're thinking of this hyperrelative theory as perturbative, in the sense of coming from string theory, the tunneling constraint is not even really a valid constraint. Huh?
Well, the thing is that if I'm thinking of it, if I'm doing string theory, then I'm typically working, right around the origin. I'm saying there's some kind of epsilon expansion around the origin. When I write my formulas, I don't want to do an epsilon expansion. I'd like to sit here at finite lambda. But if you like, all of these formulas that I write down, if you're unhappy with that idea, you can just take those formulas I wrote down and make an expansion around the origin.
I'm saying that the tunneling argument is, so all the things that you say on the next slide
Well, they're saying if I really want to sit here at some finite coupling, then you know, this theory does have unusual properties. I'm not selling it. I'm just saying I wanted to be fair and say there's stuff out in the literature. But in particular, these folks are saying, you know, there are new degrees of freedom sitting there, you know, not at some, you know, distant UV scale, which actually you could have already argued, and I'm not going to be able to, you know, that the theory becomes strongly coupled at some new scale in the UV. That's I've forgotten. It's some combination, though, of the ADS curvature scale and the Planck scale. So it seems like it's still very far away. What they're, I went the wrong way. What these folks are saying is, well, you know, the new physics is actually right there at the curvature scale. And so you should be worried. All I can say now is that, you know, a question that I asked them is, well, it seems like there are questions that you can ask of the toy model and get reasonable answers. They're afraid that there are questions I will ask and I'll get crazy answers, or answers that don't accurately reflect the physics. I don't know how to define what are the good questions and what are the bad questions. Well, in my mind, it's an interesting question, or it's an interesting thing to study. But in particular, I'll just say as a caveat, because I'm going to carry on and tell you about our calculations anyways, that perhaps these higher spin fields just aren't excited in our holographic RG flows, because they're very simple backgrounds that have a lot of symmetry. In particular, the geometries that I'm looking at are entirely conformally flat, even though they're, well, they tell us some interesting. But there's an open question mark there, and so I'm just saying that's there, and I'm going to carry on. So this was my favorite theory. I made one small change here. I put an alpha there, and what that's supposed to represent is I'm not going to couple this just to a cosmological constant. I want to say that there's some scalar field with a potential, and at the stationary points, it's going to give me something like a cosmological constant. And that alpha then is going to distinguish these different stationary points. Then I also had my two dimensionless couplings, one for curvature squared, one for curvature cubed. And so you can start to calculate. One thing is that if you sit in at one of the stationary points, you're going to have an ADS vacuum. This isn't really the curvature scale, but rather it's this combination, no, it's not even that combination. It's this combination of things. And that F infinity is some parameter that solves this cubic equation. Here's where you can see that there are going to be many branches. If I have a cubic equation, I can imagine there are going to be 3 solutions to that equation, but only one of them is the one that is going to, where I'm going to recover F infinity equals alpha squared when lambda and mu is equal to 0. The other 2 branches are going to wander off to infinity. F is the solution of this equation. It has that name because it appeared in the black hole metrics, but it's just a coefficient. Yeah, there's F. So that's just a nice way. If I didn't use F, then everything I wrote down would be 3 pages long. So this is a nice way to package the formulas. But it's a function of all the couplings in the theory. So one of the things you can calculate are what are A and C, these 2 central charges, and you can see that there are 2 formulas here, and they're different because of our higher derivative couplings. And so we've established then here's this might be an interesting framework in which to study the behavior of RG flows when I have different A's and C's in the boundary theory. So again, this was our metric ansatz for the flow at an ADS vacuum. It's that conformal factor is linear in R, and these are the central charges. And so I want to build a flow function which is going to reduce down to the central charge when I get to one of the stationary points. And so I want to write down, well, what I'm writing down here is this is what I would have had in Einstein gravity. But there must be some new stuff that gives us factors, you know, involving the lambdas and the mu's. And so the simplest stuff you can write down is actually something like this, where I have extra contributions involving, again, the derivative of that conformal factor. And so by construction, when I'm at a stationary point, this is just a constant, and this A of R gives me that quantity here, and this C of R gives me that quantity there. So that's just by construction. That's the simplest thing I could have thought about. In principle, it might, you know, I could think about far more complicated flow functions, but we're going to focus our attention there. Again, I'm going to play the game that we played in Einstein gravity. I take the derivative of my flow function. I get an expression like that. And now a miracle occurs. This is actually proportional to one of the gravitational equations of motion. And so I get to replace it by the stress tensor that's, this is the matter field stress tensor, or the scalar, that's generating the flow. If I have the null, well, the scalar would automatically satisfy the null energy condition, but assuming in general, if I have the null energy condition, then I get A prime greater than 0. And so this A thing is going to satisfy one of these A theorems. I can play the same game with the thing, this flow function. I get this. That was easy enough. But it turns out that's a big mess. It's not proportional in any simple way to one of the Einstein, or one of the gravitational equations. And so we're left with an expression where we can't really say that I'm going to end up that C prime is greater than or equal to 0. I can't really say what the sign of this is going to be because it's a big mess. In principle, we could try and be more creative in defining that, but at the end of the day, we didn't find a definition of a flow function that reduces down to C at a fixed point and satisfies some monotonicity. So it seems then like our toy model here is giving support for Carty's A theorem, i.e. there's a particular central charge that is always going to satisfy the monotonicity. And in this case, we're able to distinguish that it's A, not C, that's going to satisfy that. Again, D is a dial, and we can, having seen that work, we can reverse engineer A theorems for our other theories. Turns out that we just write down something like that. This is the gravitational equation, so that was the key step. And so from this, I basically integrate to get the flow function. And so this is going to be my flow function. And just by construction, the derivative of that is going to be positive, assuming the null energy condition. And so I have a C theorem for my theory in any number of dimensions. You might ask, you know, how robust is this? I mean, I picked some, well, my favorite toy model of higher curvature gravity, and I found this C theorem being satisfied. But you can go on and you can look at other theories involving different kinds of interactions. And again, what you find is that there's a C theorem. And something that these all have in common is that I'll call them unitary holographic models. And the idea here is that they're higher curvature. If I have a higher, that would naturally lead to higher derivative equations of motion. If I have a higher derivative equation of motion, here, say, for a scalar field, the problem with that is it leads to, in the particle physics lingo, a propagator where I have nice degrees of freedom, in this case a massless degree of freedom, but then I have another massive degree of freedom that's associated with this scale here, where that has to, because it has that form, it has to come in with a minus sign, irrespective. So, you know, it doesn't matter what that sign is. It might be a tachyon, it might be, have a positive mass squared, but the important thing is that's a minus sign. So these degrees of freedom are ghosts. And so the point is, if you look at, well, all of these theories, all of these examples, well, there are no, well, okay, what am I saying here? in general, if I have higher equations of motion, I would get ghosty degrees of freedom in the graviton, and that would represent bad stuff happening in the boundary theory. But for these theories, it turns out that there are no such excitations in conformally flat backgrounds or in these RG flows. And so if there is bad stuff there, it's not affecting the behavior of the RG flow. At the end of the day, though, we had some complicated expression for what was flowing in terms of the gravitational parameters. And so we should ask the question, what are we actually learning about the boundary theory? But that's the end of this section. And so before I answer that question, I'm going to pause again and ask if there are any questions.
So the equations for motion here were not Einstein, but the perturbations were Einstein. Is that what you said?
Yeah, in general, I have really messy equations of motion, but when I look at the linearized equations around a conformally flat background, they're just Einstein's equations. And that's really at the heart of why you get to, or well, why the equations are under control, if you like.
Can you just repeat what you said about between unitary and non-unitary?
So I have higher curvature theories. In principle, that means higher equation, gravitational equations of motion. This is just a simple example, but I'm arguing generically that means that I have ghosty degrees of freedom in my theory. Using holography, that would mean that there are negative norm excitations or operators with negative norm in the boundary theory. That's bad. So what I'm saying is that all of these examples that we're studying have a very special property that at least around the conformally flat stuff, we don't see any evidence of negative norm junk. Sorry?
It means if you linearize about
Yeah.
that
Yeah.
particular conformally.
Yeah. So in some sense, they might be there, but they've decoupled. Like if I have a more complicated background, it may be that they come into the theory again and mess up my physics. But it seems that my study of RG